Hi, I hope you guys are doing well. This is our sixth lesson, the last lesson of this unit, and today we're going to talk about probability when we have combinations. And so some of this you will have seen before, but some of it's going to be a bit new, so don't rush through it, but feel free to, try some of these questions without listening to me and see how you do. So just as a reminder, combinations are the same as permutations, but it's when the order of the situation doesn't matter. So when order does not matter. So lots of scenarios where that's the case. So for example, almost always it's with groups of items. Groups of items where you don't have any designated place for them. So for example, if I just wanted a group of 4 people, I don't care who's first or fourth or whatever. Whereas if I said I wanted 4 people and I've got specific positions for them, let's say one is the first place winner, a second place winner, and so on, then the order does matter. So things like hands of cards, the order doesn't matter. It doesn't matter if I get something first, second, third, and so on. So there are situations, and we're going to look at them where it gets a bit tricky, but hopefully you can reason your way through this. So the first thing here, it says, how many ways can you have 3 heads in 4 flips of a 2-sided coin? So no probability involved in this yet. But imagine you just want to know how many ways can you have 3 heads and 4 flips. You could use a tree diagram to do this, but we're going to start to move away from that. And I want you to think of this. So let's say we took the long way and we said we're going to list all of the possible outcomes. So you could have a head, 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 tail, right? There's a possible way. Or you could have head, head, tail, head. And you keep going, head, tail, head, head. Or you could have a tail first and then, head, head, head. I think that's all the ways. That's 4 ways. Now, if you imagine, I think the first lesson of the second unit, we talked about, imagine you had four letters, so H, 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 T. How many ways can you rearrange those letters? And so we had 4 letters, but 3 of them were repeating. That's 4 factorial over 3 factorial. That gets you 4. So you can think of this in several ways. This is really the same as you have 4 total items. So in this case, 4 flips. That's N. So I've got N, C, and I want 3 of them R. So NCR, which in this scenario, 4C3, gets me the same answer. This is really 4 factorial over 4 minus 3 factorial, and then you would have 3 factorial. So it really becomes 4 factorial over 1 factorial, 3 factorial, and the 1 factorial doesn't do anything. So you could change this. Let's say you had 5 flips and 3 heads. It still will work. You just take the total number of, in this case, flips, 5, C3, you plug it in, and you get 10. To create a tree diagram with 5 flips would be really cumbersome and long, and it'd be easy to make a mistake. So how can this be used to find the probability? So let's say we have what's the probability of flipping 3 heads in 4 flips? So same scenario as above, but now in probability. So you can think of this in a couple different ways, and showing you a couple different ways sometimes can be more confusing, but you can really think about this. So if you need to, pause the video at some point. So you got probability of 3 heads, 1 tail. The first way I'm going to show it is based on what I just showed above. The total number of ways that you can have 3 heads and 1 tail, there are 4C3 ways, or it just comes out to 4. Divided by the total number of possible outcomes of this scenario, where you flip the coin, first flip, you've got 2 outcomes. The second flip, another 2 outcomes. It's third, 2 for each one. So you have 2 times 2 times 2 4 times, or 2 to the exponent 4. And so you get 4 over 16, which gives you simplified 1/4. That is one way to think of it. Another way to think of it, again, the probability of 3 heads, 1 tail, is to take the probability of each event. So in this case, the probability of head times a head times a head times a tail. So if I did that, you get probability of head like this times probability of a tail. That's supposed to be multiplication. Except you have to include the number of ways this can happen. So in this case, you go times 4C3. And that's the part you have to try to consider, is that how many ways could this happen? So if I do this, I've really got 1/2 for each of these times 1/2 and so on. And this becomes times 4. So you've got 1/2 to the exponent 4 times 4, which gets me the same answer. I'm just going to skip to the simplified version. That becomes 1/4. So same thing. There's another way to think of it is it's good. Both ways work, whatever works for you, but it's good to think of them in both ways. Okay, other scenarios where we had combinations. So again, we're going to start without probability, and we had questions like this before. In how many ways can you have 3 hearts and 2 diamonds in a poker hand, which has 5 cards? So just the number of ways. So remember, it's a hand of cards. That means the order doesn't matter. Whereas in the previous lesson, we talked about if you had, an ace and then a king and then a king, in that order, that's different. So in this hand, the order doesn't matter. So if I want 3 hearts, so we have to think about how many hearts there are. We know we got combinations, and we're going to take 3 of them. So hopefully you remember there are 13 hearts, so a quarter of the deck. And the number of ways that I have 2 diamonds, there's also 13 diamonds, and I want 2 of those. So these are my hearts. And these would be my diamonds. And we just plug them in. So we plug that into our calculator. You can try that out, but I'm just going to write the answer. I get 22,308. So more, I think, applicable is what's the probability that you get this? 3 hearts and 2 diamonds. So endless number of scenarios you can have with cards to see this kind of situation. So the probability of 3 hearts and 2 diamonds. So I've got my numerator, what I just wrote above, 13, choose 3 times 13, choose 2. And then my denominator is always the total number of possible outcomes with no restrictions. So how many different ways can I have 5 cards in a hand from a deck of 52? So really that's just 52, choose the number of cards in the hand, 5. And so I can just use this, plug it all in. And I get approximately, and I can't remember if this simplifies into a fraction, but anyway, I get approximately this, which is approximately 0.858%. So less than 1% chance. And that's why figuring these probabilities out can be pretty tricky in your head, because it's, complex numbers, or big numbers rather, and then really small likelihoods that they happen. So let's take a look at a couple other examples. It says, without probability, again, how many ways can 6 people be selected from a group that consists of 4 adults and 8 children if the group must consist of exactly 2 adults? So I think we have this exact question. And you can try this, again, I think at this point you can probably try these without watching, but then check your answer. But if you need some guidance, you can continue to watch. So again, we've got a group. The order doesn't matter, so no order. 4 adults and 8 children, and we want exactly 2 adults. So we've got 4C2 because there are 4 adults, and we want to pick exactly 2 of them. That implies then that we have in our group of 6, 4 children added to it. So we've got adults, and we've got our children. And like we talked about a while back, it's multiplication because they're forming one group. It's not 2 adults or 4 children. It's together they're forming one group, so different arrangements of those together. So you plug that in and you get 420. So you can imagine the probability in the next question. What's the probability that given 4 adults and 8 children, a group of 6 people is formed with exactly 2 adults on it? So what's the likelihood that you have that happen randomly? So you got 2 adults, 4 children. Numerator is exactly what we just wrote. And our denominator is the total number of arrangements that you can have of any number of adults and children. So this will always be the group size, choose the size of the group. So the total number of people available, choose the number of the group size. So this is my group size. And this guy will always be whatever is available. In this case, the total number of people. So it could be the total number of cards, items, whatever it happens to be. So you plug that in and you get 420 over 924, and that simplifies into 5 over 11. Okay, the next one is kind of an extension on just that. It says, again, without probability, how many ways can 6 people be selected from a group of 4 adults, 6 children, if there must contain at least 2 adults? So if it's at least, that means you could have 2, you could have 3, you could have 4, and it maxes out at 4 only because there are just 4 adults available. So what we need is the number of 2 plus the number of 3 plus the number of 4, because it's or 2 or 3 or 4. So we go through that process. So 4 choose 2, the one we just did above, times 8 choose 4. And then see if you can get the other 2 here if you haven't paused already. But if I have 3 adults, I have 4C3. That means I have 3 children to make my group of 6. And then my last one, 4 choose 4 times 8 choose 2. And get these numbers here, 420 plus 224 plus 28, which gives me 672. Now, same question, only now what's the probability that you get this happening with at least 2 adults? So probability of at least 2 adults. One way you can do this is just to take that number, so everything we wrote above. You could also do this using the complement, which I'll talk about in a second. The question here, what's my denominator? And again, it's the total number of the group size, so 12, choose the size of the group that we want, which is 6. So we just take these numbers, so I get 672. We already had the other one. What was it above? 924. And we get approximately 7, if we wanted it as a decimal, 73. So I think on the side, oh, maybe it's not there. There it is. Oops, put it in the wrong spot. So you could do this. You could say, okay, the probability of at least 2 adults is 1 minus the probability of 0 adults and 1 adult, because that is the opposite or the complement of at least 2. And so you would take 0 adults, 6 children, 1 adult, and 5 children. And you get the same answer. Sometimes that way is quicker. I guess maybe it's slightly quicker in this one. But now we're always taking 1 minus, like we talked about with the other probability. Okay, try the U-try here. Again, pause the video or just take a look on OneNote for the answers, but I'll explain them here if you need it. So this one, determine the probability of getting 4 heads in 5 flips of a coin. So probability of 4 heads, which implies 1 tail. So the order here, we don't know which order. We've got the 4 heads and 1 tail. It could be the tail first, second, third, and so on. So this will be 5C4. So total number of flips, choose the number of heads or tails that I want. So 5C4. And you could put it as 5C1. It still works. It's the same number. So if I could say, well, what's the number of ways I have 1 tail? And that would be 5C1. And And then times 1/2 to the exponent 5, because we've got that probability, so I get 5 over 32, which I can't reduce. And the next one, determine the probability of getting 2 clubs and 3 spades in a hand of 5 cards without replacement. So probability of 2 clubs and 3 spades. So this one's really similar to what we already had above. So I've got, good to practice it, 13C2 times 13C3 over my total number of cards, 52C5. And I think we did have the same numbers, 00858, if we work it out. Okay, as usual, if you have any questions, just let me know, and I'll be there, and come to Extra Help if you can. There's some practice questions to try out, really important to do those. Okay, see you soon.